Okay, welcome to lecture here. We'll get started here in just a second. We are rolling into chapter 3. And again, the notes should be up there on Canvas. If you haven't found them, that's where they should be. And a reminder, pretty much what we are going to be talking about now is stuff that will not be on the first exam. So we're now moving to second exam material. Remember that the only thing from chapter 3 that you really do need to know from this particular chapter for the exam is just what we talked about last time, which was what electronegativity is and the general trend of it. And obviously, we're going to talk a little bit more about electronegativity in this chapter. But again, the rest of that and the rest of this chapter is part of exam 2. So technically, this all starts first exam. Yeah, I believe it will be. So I believe the first exam is scheduled for, I want to say, a week from Tuesday or something like that. So whatever it is on the schedule there, it will be on that day. A reminder, we also have a quiz coming up on this Tuesday on chapters 1 and 2. So, and I believe the exam is a week after that. So I'll trust you on the date there, 22nd. Okay, so in this chapter, there's a lot going on in this chapter that we're going to talk about, but mainly what we're going to talk about here is chemical bonding and the different types of bonding. We're going to talk about ionic bonding. We're also going to talk about covalent bonding, what those guys are. We will also talk about some new stuff probably for some of you, some things like hybridization and that type of stuff. Actually, that'll be in the next chapter, I think, after that. We will skip the last section of this and come back to a little bit later on, which is, I think, the last section of chapter 3 is nomenclature. So we'll come back to that. But we're going to cover pretty much all the bonding right now. Then we'll do the next chapter, which is they kind of go together. So that's what you could probably imagine. Everybody's favorite thing, geometry, molecular geometry, and all that kind of stuff will come after this chapter. And like I said, I think the last part of chapter 3 technically is nomenclature. And after we do a couple other things, we'll come back to the rest of that and talk about it. All right, so off we go here for bonding. So a couple important things when we talk about bonding and some of the stuff that we talked about earlier in the previous chapters, which are obviously important as well. So before we actually see that, maybe here. A reminder that bonding really does involve a certain type of electrons, and those electrons are the valence electrons. And remember, the valence electrons are the highest in energy outermost electrons. And again, you could really figure out the valence electrons by writing the electron configuration, or probably the easier way is, again, that the number of valence electrons equals the group number. So again, everybody there in group 1 has 1 valence electron, everybody in group 2, 2, and so forth, all the way across there. And we're talking about really the representative groups there, 1 through 8, that we normally talk about. Transition metals, slightly different because they are transition metals, and a little bit about sort of what we were talking about with electron configuration, that they do lose those s electrons first. So again, sometimes people consider them have 2 valence electrons, but they do have those d electrons available to them. So some people think they could have upwards of 12, depending on which one you're talking about. The good news is, in terms of bonding, we really don't do very much, if any, type of bonding that involves those transition metals. So you don't really have to worry about it in terms of bonding. Most of the bonding we deal with will be covalent bonding, and ionic bonding between sort of our representative elements and, you know, metals and nonmetals. So we do use Lewis dot symbols. They're sometimes called electron dot symbols. And basically what they are is the element symbol and basically one dot to represent each of the valence electrons that are there. Again, valence electrons involved in bonding. Those electrons that are closer to the nucleus are referred to as our core electrons. They are not involved in bonding. There's no real sort of rule per se in terms of Lewis dot symbols or electron dot symbols. So if this X represents the symbol, really the only sort of rule is no more than 2 dots per side. So most people kind of go around and then, you know, sort of pair it back up. But in reality, there's, you know, not really truly any real rule there. The main rule is no more than 2 per side. And as you can see here, if you max out all the sides of the symbols, we would end up with 8 electrons. And the guys on the periodic table that have 8 electrons is our noble gases. And if you remember some stuff from bonding, 8 is a kind of an important number. And as we talked about with electron configuration, that really is sort of the whole point of bonding, is for everybody basically to end up like our noble gases, which is group 8 on the periodic table. Again, that's a very stable sort of situation, and that's ultimately what people are trying to reach through bonding. Both types of bonding, ionic bonding, covalent bonding, really the ultimate goal. Everybody hits that sort of 8 magical number, except for hydrogen, for example, but everybody else pretty much needs 8. So we could use Lewis dot symbols or electron dot symbols really to sort of help us understand what's going on with bonding. And like I said before, 1 dot for each of the valence electrons. It's also important to remember that although we only show valence electrons in Lewis dot symbols or when we draw Lewis structures, obviously these elements still have all their other electrons still there, those core electrons. Again, because of those periodic trends and stuff we've been talking about, they're very much held tight by the nucleus, so they're not able to really be involved in bonding. So again, that's why it's just those valence electrons that are involved. Here's something I made when I was bored. I really should get a hobby, but here we go. Here it is, the symbols and our dots there. So you can see everybody there in group 1 has 1 valence electron. Everybody in group 2 has 2 valence electrons. 3, 4, 5, 6, 7, 8. Helium here, which is group 8, it only has 2 valence electrons, and that's because helium only has 2 electrons total. So obviously it can't have 8. And the same deal with hydrogen as well. It obviously has 1 total electron, so it only has obviously 1 valence electron as well. So this is a good way to do it. You can see here again, pretty much no more than 2 per side, and that's usually how we do represent them. Like I said before, pretty much don't have to worry about anybody in the transition metal region. Again, most folks sort of consider that they have kind of 2 valence electrons, but as we talked about, when they do lose electrons, they can go into those d electrons. So again, sometimes they'll be thought of as having upwards of 12, sort of depending on which one you're talking about. So let us talk about ionic compounds. And as we sort of talked about it, when we talk about Lewis dot symbols and structures, there's really 2 types of compounds that come about. One is an ionic compound, and ionic compound will always be a metal and non-metal coming together. And what happens in this situation is, again, the metal will transfer that electron over to the non-metal, resulting in our metal becoming positively charged or a cation, while the non-metal, which says thanks very much, picks up the electron, now has extra electrons, extra negative charge, becomes an anion, and it is that attraction between these 2 guys here, that electrostatic attraction, which holds that together. So as I might have mentioned earlier, and I'll mention several times, I'm sure, before we're done with these chapters, a reminder that there's absolutely no sharing of electrons that are happening when we're dealing with a ionic compound. We have a complete transfer of electrons from the metal to the nonmetal. And that's very different than a covalent compound, or sometimes it's referred to as a molecular compound. And that is when we have two nonmetals. And when we have two nonmetals that come together, the difference is there is actual sharing of electrons. So what holds those guys together is the two atoms decide we will share electrons, rather than in the metal non-metal case, they will not share electrons. And as we'll talk about in this chapter, that sharing may be equal or, again, unequal sharing of those electrons. And really a lot of what we were talking about the other day about the periodic trends is really why we have these two types of compounds that form. So if you just think about looking at sort of the periodic table, metals are essentially on the left-hand side, right? And nonmetals are like upper right. So when a metal and a nonmetal pretty much come together, what you have there is pretty big differences in terms of all those periodic trends we talked about. Differences in ionization energy, differences in electronegativity, electron affinity. So what you have when those two guys come together is you have the metal on one hand is like, I don't really want to hang on to my electrons. I'm not really caring about them. And you have the nonmetals who are like, I like electrons. I'll take them. No problem. So when those two guys come together, essentially what happens is we get that transfer of electrons that happens from the metal, which really you don't have to convince it very hard to give away its electrons, to the nonmetal, which you don't have to convince very hard to accept those electrons. And that's very different than if we get two nonmetals together, because two nonmetals together are pretty much in the same location there on the periodic table, which means they're going to share pretty similar periodic trends that we talked about. They both, in the case of nonmetals, are going to go, I want electrons, right? And they're both going to pretty much go, I don't want to give up my electrons, you don't want to give up your electrons. So sort of the best that they could kind of settle on is, all right, I'm not going to completely give up my electrons. You don't completely give up your electrons. I'm sure this is the conversation that happens between them. And then they decide, well, we'll just share. So the best that they could kind of do is sharing. And in some cases, they're very friendly about it. They will share equally. In other cases, one guy's like, I'm going to share a little bit more than you will in that particular case. So that's why when we do get two nonmetals together, because they have very similar periodic sort of trends and properties, the best that they can sort of settle on is sharing of those electrons. While when we get metals and nonmetals, which have a very wide difference in those periodic trends, we're going to get that complete transfer of electrons. So the general rule is, in terms of sort of ionic compounds, is things with very low ionization energies, which, if you remember from last lecture, is the energy required to remove an electron, tend to form cations, and our low ionization energies are found on the periodic table left and down. So to the left and down on the periodic table, ionization energy decreases. And those with high electron affinity tend to form anions, and where that is on the periodic table, like we talked about, is up and to the right. And up and to the right is our nonmetals. So when, again, those two guys get together, you pretty much have a metal that's willing to give away its electrons. You have a nonmetal that's way willing to accept those electrons. And again, that's why when those two guys come together, we do get those transfer of electrons that basically happen. So general rule, kind of like what we've been talking about, again, things in group 1, group 2, group 3, for example, will tend to form cations, positively charged guys, while our nonmetals upper right there will typically be our anions and make our negatively charged guys. And again, our metal is going to be giving our electrons away to our nonmetal. So let's take a look at how this sort of happens, if you will. And we could use, again, these Lewis dot symbols to help us understand it. So when we have something like lithium fluoride, if we were to look at the electron configuration for lithium fluoride, lithium is 1s2, 2s1. Fluorine is 1s2, 2s2, and 2p5. So again here, if we look at it, lithium, which is group 1, this is its valence electron right there. Fluorine, which is group 7, that is these 7 electrons right here are its valence electrons. So again, if we sort of started with our symbols here, we would have a lithium that has 1 dot. We would add it to a fluorine that has 7 dots around it. And again, in this case, we have a metal and a non-metal. So what's going to happen is the electron from the lithium will transfer over to the fluorine. And when it does that, what's going to happen is my lithium now has lost that electron. And that is when it actually will gain that positive charge when it lost that electron. Now our fluorine will pick up that electron and it will now have 8 electrons around it. And in addition to that, it will pick up a negative charge. And when we draw something like this, which is an ionic compound, we do want to include the charges here because these are 2 guys that have charges. And when you draw the Lewis structures for ionic compounds, you should include the charges. What that indicates is that there is no sharing of electrons here. The electrons have been transferred from the metal to the non-metal. Also why sometimes people will put brackets around both of them or one of them like I did here. And that's what we see kind of going on. So what happens when we look at the actual sort of electron configuration for both of these guys? So originally they both started out like we see up on top. And on the right-hand side, after lithium loses his electron, it now will end up losing, obviously, this electron here. And it will end up with a configuration of 1s2. 1s2 is 2 electrons. And if you look on the periodic table, that is the same electron configuration as helium. That 1 electron is going to head over here to this subshell and is going to add into there. And our fluorine, which is fluoride, will now be 1s2, 2s2, 2p6. And again, if you count up the top numbers there, that is 2, that is 4, that is 6, that is 10, I believe, at that point. And 10 is neon on the periodic table. And as I mentioned before, the whole basis of any type of bonding is for everybody to end up just like these guys. And these guys, as we hopefully know, right, are our noble gases, right? So they end up being isoelectronic with those noble gases. Again, a reminder that isoelectronic means that they have the same electron configuration as something else. So in this case, they have the same electron configuration as, as the noble gases. Question on that there. There's my scribble there. Let me see here. So the whole group. So if you're asking about for fluorine in terms of the valence electrons, you're asking about these guys here. Yeah, so remember that what valence electrons are the highest energy level. So when we look at something like that, and I write the electron configuration correct, let's try that again. That's my first day. We'll try it that way. When we look at this first number, that's basically the first energy level. So on the first energy level, there's 2 electrons. Now, although there's s orbital and a p subshell here, they're both on the second energy level, which is the highest energy level. So the 2 there and the 5 there would be the 7 valence electrons that would come from there. And again, the easy way to remember that is just as fluorine's group 7. So it would have 7 valence electrons, but it is these. So it's not necessarily just the very last subshell, for example, that you write in the electron configuration. It's all the electrons on the highest energy level. And in this case, they're both there. Yeah. Other questions on that? Okay. All right, so what is holding that together, again, as I mentioned there, between the lithium with a +1 charge and the fluoride with a -1 charge, again, is absolutely no sharing of electrons. It is that electrostatic attraction between the positive and the negative ion. And again, that is basically what is referred to as an ionic bond. So ionic bond, and you don't really need a lot of information to figure out this is an ionic bond or not. It is a pretty darn safe bet that if you could recognize one thing as a metal and one thing as a non-metal, it's going to be an ionic bond. There's going to be no sharing of electrons. We're just going to have this positive and negative attraction that's happening there. So let's take a look at another example, which is calcium and oxygen. And in this particular case, calcium, which is group number 2, so it has its 2 valence electrons here. Oxygen, which is group number 6, has its 6 valence electrons. And again, if we look at the electron configuration for calcium, it is argon 4s2. And again, these 4s2 guys are the valence electrons. If we look at oxygen, it is 1s2, 2s2, 2p4. And in this particular case, what's going to happen is calcium is going to give away 1 electron, say there. And if you just look at the periodic table, so for example, calcium is here, next to calcium is potassium, and then we come back to argon, right? So when calcium gives away 1 electron, it really only moves it back to potassium. So it wants to give away 1 more electron so that it could end up back at argon. So the second electron here is going to go over to oxygen, because again, here oxygen can accept both of those. And when calcium does lose its second electron, it does become positively 2 charged because it lost 2 electrons. The oxygen will gain those 2 electrons and become negatively 2 charged. And again, here, what is holding this together is that attraction between the positive 2 and the negative 2. Again, no sharing of electrons. So if we look at what is happening with our electron configuration as this process occurs, again, the calcium is going to lose its 2 valence electrons, which is this guy. That's going to take it from 20 electrons down to 18. And as we can see there, 18 electrons is our good friend argon. And those 2 electrons are pretty much going to go right into the empty spots there in the p subshell. And that's going to bring our oxygen to 2, 4, and 6, which is 10. And that's going to bump our oxygen here with a -2 charge up to neon's configuration. So again, here you can see that by sharing electrons, not really sharing electrons, I'm sorry, transferring electrons, the metal losing the electrons and the non-metal gaining the electrons, both of these guys have now reached the noble gas configuration, the really sort of stable situation. And again, that is ultimately the goal here of everybody. Question on that there. So again, you see the charges on the right-hand side. Again, you should always include those when you're drawing any type of Lewis structure that involves ionic compounds, to display that they are not sharing those electrons, but are transferring the electrons. Now, if we look at maybe 2 of these things that we just looked at, let's say we take our good friend calcium, which as we saw has 2 valence electrons with our argon 4s2 configuration. And we take our fluorine that we saw earlier, which has 7 valence electrons. So what happens when we go to put these 2 guys together? So fluorine, again, going to have our 1s2, 2s2, 2p5. And what's going to happen in this case is our calcium is going to lose its electron. But the problem is what we were just talking about. If calcium only loses 1 electron, like we saw on the previous page, he's now only moved to potassium's configuration. And alkali metal configuration doesn't have as nice a ring as noble gas configuration, right? So he still needs to lose one more electron. The deal is, though, this guy at this point is now pretty much full. He's got 8. So what we need in this situation is not just one fluorine, but we actually need 2 fluorines here. And that second fluorine now has the room to take its second electron there. And what ends up happening in this case is we do form a calcium with a +2 charge. And we end up with a fluorine that has gained 1 electron and becomes -1 charge. And we end up with a second fluorine that has gained 1 electron and has become now -1 charge. This is why, as you may remember, when you put something that is positively charged together with something that is negatively charged, they always tell you it needs to equal 0 in the simplest way to equal 0. And the correct formula for something like this is calcium fluoride, CaF2. And the reason that we actually do need the 2 is really for this reason. If we only had one F, calcium will never make it to the noble gas configuration. It needs both fluorines here to actually end up at the noble gas configuration. So that long sort of story of where they tell you you need to balance out the charge, get it to 0, the real reason is this reason right here. By balancing it out to 0, putting it together with a charge of 0 in the simplest way, what that's essentially going to do in terms of a bonding perspective is allow everybody there to end up in the noble gas configuration. And we see that here, and we could verify that by looking at what we did before. Calcium again has lost these 2 electrons, which means the calcium here has now hit argon's electron configuration. This fluorine here picked up 1 electron, which means that got this fluorine to 10 electrons, which got it to neon's configuration. This guy here also picked up 1 electron, which got this guy down to 10 as well, and also got this guy to neon's configuration. All 3 of these guys in this ionic compound have now hit noble gas configuration, and that again is going to make them very stable and very happy. And that is really the reason why when we talk about nomenclature and writing formulas for ionic compounds, why you always want to balance out the charge to 0, and you always want to balance it out in the simplest way that will get you to 0. Because in the simplest way you could get to 0, that is the lowest way that you could get everybody into the noble gas configuration. Any questions on ionic compounds, how to show the bonding, what's going on any of that? Okay, so that is ionic compounds. Definitely always the situation here when we're doing metals and nonmetals together. So I think we're going to now talk about covalent bonding, what happens when we actually put 2 nonmetals together and sort of what's going to go on there. So let's talk about a covalent bond. And again, a covalent bond is what is going to occur when we do put our 2 nonmetals together. And as I talked about at the opening, the real reason for that is, and why it's different than ionic compounds, is now we are taking really 2 elements that are pretty much in the same location on the periodic table, which means they're going to have extremely similar periodic trends, especially those trends that involve electrons and either getting rid of electrons or hanging on to electrons. They're going to have a very similar type of properties. And what that means is the best that they could kind of do is share those electrons, rather than what we get when we put a metal and non-metal together, that we have those very big difference in those properties. We get that transfer of electrons that occurs. So here we have hydrogen, which has 1 electron, and another hydrogen that has 1 electron. And clearly they are both hydrogen, which means they definitely have the exact same periodic properties. So what's going to happen here is neither one of them is really going to want to give away their electron. So these 2 electrons are basically going to come together, and they're going to share these electrons. So what we end up getting is you know, basically 2 electrons being shared by the hydrogen on the left and 2 electrons being shared by the hydrogen on the right. And even though this is hydrogen and there's just 2 electrons, this hydrogen on the left technically has 2 electrons. This hydrogen on the right has 2 electrons. And if you reference your periodic table, our good friend on the periodic table with 2 electrons is helium. Yeah. So in this particular case, by actually just sharing 1 electron with the hydrogen on each side, they both end up with 2 electrons. And what that essentially does is move hydrogen to helium's configuration, which is a noble gas, and it makes it very stable and very happy. That's a very important rule for hydrogen. Hydrogen only needs 2 electrons, which means it only needs to get to helium. Everybody else needs 8 because that gets them to neon and beyond. But hydrogen should only have 2, which means this is pretty much what hydrogen should look like here. The sharing of electrons is what is known as a covalent bond. In this case, we have the electrons being shared between these 2 hydrogen atoms. And again, they do sort of count for each of the hydrogens. You can represent it with these 2 dots, or you can represent bonding electrons there with a line, like so. Again, the line represents 2 dots are a pair of electrons, right? That's a single bond. And again, 1 line, 2 dots are a pair of electrons, grand total of 2 electrons there, and being shared between these 2. So in a covalent bond, because they both, again, do have very similar sort of properties, what ends up happening, if you sort of think about it, is you have these electrons are attracted to the nucleus of one atom, but yet they're attracted to the nucleus of the other atom. So what that ends up doing is sort of locking them in place, and they're not able to obviously kind of escape that because of that mutual attraction between everybody. Now, F2 here, if we look at F2, again, the electron configuration, 1s2, 2s2, 2p5. The same thing's going to happen here are 7 valence electrons in each. They're both fluorine, which means that these electrons here are going to be sharing each other. And we can represent it one of 2 ways here. You can, again, either represent it with the dots. And again, on this side, if we count it, the fluorine on the left has 8 electrons. Those electrons in the middle are going to count for the fluorine on the right, which also has 8 electrons. And here they both reach 8 electrons, which again basically moves them to that noble gas configuration, again making them very happy and stable in that case. Now, when we do look at sort of fluorine here, there's really a couple different types of electrons that we see in this. Pretty much all the electrons that are around the end here that does not have anything written next to it, no other element next to it, they're not involved in bonding, and they have a very creative name. They are known as non-bonding electrons. So these are non-bonding electrons here. And if you're old like me, they call them lone pairs still, some people. So somebody says lone pairs, or somebody says non-bonding electrons. They're basically talking about the same thing. Electrons that are not involved in any type of bonding. I personally will probably say lone pair a lot because that's just what's in my head, but people do use non-bonding electrons more so. The electrons that are actually being shared between the 2 atoms also has a very creative name. It is known as the bonding electrons here. So that is the bonding electrons. So the electrons that are being shared between atoms are bonding electrons. Electrons that are not involved in a bond are known as non-bonding electrons, or lone pairs. You should always include all those type of electrons in your pictures when you draw your Lewis structures. So again, a Lewis structure is a representation of bonding, again, using those Lewis dot symbols, and a reminder that really only the valence electrons there are being shown. We still have all those other sort of core electrons involved, not really involved in the bonding, but are still present. But again, they're not truly involved in any of the bonding that's happening there. So here, if we look at another example, this is water. And here water is sharing some electrons between the hydrogen and the oxygen. And by sharing with the oxygen here, each of the hydrogens end up with 2 electrons. And the oxygen sharing with both of those guys end up with 8 electrons, as you can see down here. And all 3 of those things, the 2 hydrogens, the 1 oxygen, the oxygen has reached 8 electrons, just like the noble gas. Hydrogen, as you can see there, got to 2 electrons, which is the maximum it should have. So again, a reminder that you should never draw a hydrogen like this with all those electrons. You should never double bond like a hydrogen. You should never triple bond a hydrogen. Otherwise you're just going to get maybe a big one of those. So hydrogen pretty much going to be like that, or again, 2 dots into another element, but never should have dots around it or anything like that. Again, hydrogen only needs those 2 electrons to get to the noble gas configuration. So obviously, as you can see, 8 is a really important rule, and that is our very famous rule in terms of bonding, which is our octet rule. And the octet rule basically means that everybody will continue to make bonds until they have 8 valence electrons around them. And they'll continue basically to share electrons, make bonds, whatever they need to do really to get to that 8. Again, the one exception for that is hydrogen. It only needs 2. And that is sometimes what is referred to as the duet rule. Just 2 electrons, just like I just drew on the other page. No dots around hydrogen, no triple bonding to hydrogen. I don't know what it is with hydrogen, but people just like to keep on piling on lines and dots and stuff with them. So make sure that you don't do that. So let's talk a little bit about double bonds, single bonds, and triple bonds. So good talk. Let's talk a little longer maybe. So as I mentioned before, a single bond is a representation, either 2 things. You could either use a line for the bonding electrons, or again, the 2 dots there for our bonding electrons. Again, it is sharing a pair of electrons or 1 line. And again, in that situation, that's going to allow everybody really to get to 8. But there are certain cases where single bonds will not do the job in terms of getting everybody to 8, that you actually do need double bonds. And a double bond can be represented by 2 lines, or again, 2 pairs of dots. So obviously each line represents 2 electrons, 2 lines represents, as you can see here, 4 total electrons. And CO2 is an example of that. In order for CO2 to properly get everybody to 8, it needs to share some electrons with the carbon on each side for the oxygen. And then the carbon needs to double bond up with everybody. And again, as you can see over here, that allows everybody there to get to 8 electrons and be happy with what they're looking for. And lastly, sometimes it does take a triple bond to achieve that. And here's a couple of examples of triple bonds. And again, a triple bond is represented by 3 lines, are obviously 6 electrons involved in that. And again, in the case of nitrogen here, that triple bond in the middle is 2, 4, 6, and 8 electrons on the outside. Again, 2, 4, 6, and 8 electrons on the other side. And everybody there has 8. Same thing down here. We see the carbons are triple bonding to give us 6 electrons there and 2 more there for 8. And again, 6 electrons there and 2 more for 8 for that carbon. And our hydrogen has just 2 electrons on both sides when we look at it here. Any questions on that there? Okay. So now we're going to talk about then electronegativity, and electronegativity a little bit more than sort of what we talked about it in terms of the general trend. We obviously talked about it in the last chapter, and electronegativity again is that ability of an atom to bring electrons towards itself. And again, as we talked about, and we'll see here one more time, it increases as you go up and right on the periodic table and decreases as you go left and down on the periodic table. Again, fluorine being the most electronegative element that we can have. So electronegativity really does help us distinguish what is going on between what type of bond that we would expect. Will it be ionic bond? Will it be covalent bond? In a covalent bond, will that covalent bond be sharing the electrons equally? Will it be sharing the electrons unequally? You know, any of those type of things. Electronegativity really is sort of what will help us sort of decide what's going on there in terms of how those electrons are going to be shared and what we can expect in terms of the type of bonding that will happen. So let us take a look at some examples here. Obviously, if we had something like H2, they are both hydrogen. And when they do come together, because they're both hydrogen to form that bond, you know, we would expect the electrons, if this really bad circle here is the electron density, that the electrons would be shared relatively equal between those two hydrogens. Again, one hydrogen is going to pull just as much as the other hydrogen. So those electrons in the middle will sort of spend equal amount of time between the different hydrogen atoms. And we would expect that the electrons would be shared equally. Now, what happens if we actually take away a hydrogen and replace it with something like fluorine? Now, fluorine, as we talked about, is more electronegative. So when these two guys really come together, we really would not expect the electrons to be shared that equally. And because fluorine is more electronegative, we would expect the electrons to kind of spend more time over on the fluorine side than, say, on the hydrogen side. And what that's going to do to a bond like that is it's going to sort of separate what is known as the charge here. So essentially what's going to happen is the fluorine, because it's going to have more electrons hanging out near it, is going to become more negative, and it will get a partially negative charge. And that's a little delta symbol. And the hydrogen, where the electrons are basically moving away from, will essentially get a partially positive charge on it. And we get this because, again, the electrons are spending more time on one side of the bond versus the other side of the bond. And this gives us a different type of covalent bond. This is what is known as a polar covalent bond, or just known as a polar bond. And so our case of HF here, partially negative, partially positive, unequal sharing of electrons. Is known as a polar bond. Most people will just call it a polar bond. And that is different than our two hydrogens, where we have equal sharing of electrons. And this is what is sometimes referred to as a nonpolar covalent bond. Or most people will just call it a nonpolar bond. And same thing would happen if we had two fluorines like we saw earlier. We would expect it to be shared equally. This also would be a non-polar bond. So a polar bond occurs when we get two elements that are still sharing electrons, but they're sharing them unequally. And that is why when we talk about charges here, these are what are referred to as partial charges. They're partial charges because the electrons have not completely transferred from one side to the next. They're still hanging on in terms of some type of sharing that's occurring. But again, the sharing may be unequal sharing, obviously, and that's why we get these partially positive side and partially negative side, again, represented by that delta symbol. So nonpolar bond, equal sharing of electrons. Polar bond, unequal sharing of electrons. And in a polar bond, that is where we develop a partially positive side of the bond and a partially negative side of the bond. As we can see here by my wonderful pink spread here, electron cloud. Again, more of the electron cloud is over here on our fluorine side. Another very common way that we represent this unequal sharing of electron is to use arrows like we see on the bottom here. And these are what are sometimes referred to as dipole arrows. And it basically points to the side that is more negative in the bond. And the little back part that kind of makes like a plus sign is the side that's more positive. And these are sometimes, again, referred to as dipole arrows. Or some people will call them bond dipole arrows. And it really is the electronegativity that helps us sort of decide, you know, are we going to get some sharing of electrons? And B, are sharing of electrons going to be equal or unequal? And we'll talk about how we can sort of figure that out in just a second and what we use for that. So as I mentioned before, we have this unequal sharing of electrons creating these partially positive charge on one side where the electrons are sort of moving away from, or partially negative on the other side where the electrons were moving towards. And you could kind of think about the three types of bonding that we sort of have talked about here. And let's talk about that. I'll put it here. Sort of on one end of the extreme, we have an ionic bond. And again, an ionic bond is going to be your metal and non-metal. And as we talked about, that is where we're going to get that transfer of electrons, going to make our cation and our anion no sharing of electrons at all. That's a negative charge there. Try that again. Negative. On the other end of the stream, we have really a non-polar bond or non-polar covalent bond. And that is between two nonmetals where we have equal sharing of electrons. And an example of that would be something like F2 that we just saw, or H2. And sort of in the middle is a polar bond. And in a polar bond also between two nonmetals. And we have also sharing of electrons, but the sharing is unequal sharing. And an example of that would be like HF here. So these are really sort of the three types of bonding that you come across. One side all the way to the left there, ionic bond, they have such differences in properties that we get a complete transfer of electrons, no sharing of electrons at all. On the other end of the extreme, we have a non-polar covalent bond where we have two nonmetals that have similar, very, very similar properties, going to share those electrons equally. And lastly, sort of in the middle is we have two nonmetals that have similar properties. They're still going to share their electrons. They're not so dissimilar that electrons transfer. They're still hanging in there in terms of sharing, but the sharing is unequal in that particular case. Any questions on those sort of three types of bonds or bonding that's happening here? Okay. If you have questions, feel free to ask. All right, so let's get into then what is going on and how we determine whether or not something will be polar, nonpolar, or sort of ionic. So as I mentioned, it really is the electronegativity that helps us understand the type of bonding that we're going to see. And as we talked about a couple of times at this point, electronegativity is that ability of an atom to bring electrons towards itself. And again, electronegativity is based on electron affinity and ionization energy. So remember that electron affinity is the energy change that occurs when something gains an electron, while the ionization energy is the energy required to remove an electron. So something with very high electronegativity will have a very high electron affinity and a very high ionization energy, while something with low electronegativity has the opposite there. I'm not sure I got an extra O there. We'll get rid of it. So fluorine, for example, upper right of the periodic table, pretty much means it has very high electron affinity and has very high ionization energy, all of which means it really does like to grab onto those electrons. And opposite of that is sodium, which is way over on the other side. And to the left, we're going to have something with very low ionization energy and low electron affinity, which essentially means it's willing to give away its electrons and it'll be perfectly happy kind of to do so. Now, there was a guy named Pauling, and Linus Pauling, he came up with sort of a numerical value to help us understand electronegativity. And the numerical value for electronegativity is essentially, runs from 0 to 4. 4 is the most electronegative, 0, not so much. Do that scientific word there, not so much. You hear that a lot in science. And here, if on the periodic table, as we will see, our good friend fluorine has a value of 4. So that's why it is really the most highest in terms of electronegativity. It has the highest sort of electronegativity value. And again, our general trend is, again, increases as you go up to the right on the periodic table, decreases as you go left and down. And we can use the differences in electronegativity to help us determine if a bond is polar or nonpolar or even ionic, although in terms of ionic, you really can sort of figure it out because it is a metal and a non-metal. So here's a table of electronegativity values. And for example, there is sort of a cutoff that most people use to determine whether or not a bond is polar, nonpolar, or ionic. And we do what is sometimes referred to as delta En. That is a fancy way of saying the change in electronegativity value. So that's basically what that means. And if you do the change in electronegativity value and you have a value of 0 to about 0.4, that is usually considered a nonpolar bond. If you have anywhere from above 0.4 to below 2, that is some type of polar bond. If you have a difference that is typically above 2, that is an ionic bond. Like I mentioned before, in terms of an ionic bond, you pretty much don't need the electronegativity values. If you see metal and non-metal, it's ionic. You don't actually have to really calculate it. But usually electronegativity is very helpful for, is it a polar bond? Is it a non-polar bond? Remember that a polar bond and a non-polar bond are covalent bonds. So these are electrons being shared. So if we look at some of the examples that we saw earlier, if you remember, we had sodium chloride. If I go to the table here, I see that the electronegativity value for sodium is 0.9. And if I go to it for chlorine, that is 3 over there. So if I take the difference in electronegativity, it is as easy as subtracting. So 3 minus 0.9. I'm going to do it without the calculator. I'm going to go with 2.1 and hope for the best on that. So 2.1 is definitely above 2, which means we would expect this to be an ionic bond. Like I mentioned before, you could pretty much know it's sodium and chlorine, so that's a metal, non-metal. You really don't have to worry about it. You'll know that it is probably going to be an ionic bond. Now, if we look at one that we had before, like fluorine and fluorine, we go to the table, we see that fluorine has a value of 4. This fluorine has a value of 4. So if we take the change in electronegativity, that is 4 minus 4. And try again without the calculator. That's going to be a 0, I think, in this point. And that tells us that this is going to be a non-polar bond. Well, this guy was ionic, obviously. This would be a non-polar bond. Now, just a note on a non-polar bond. When you have a difference in electronegativity value such as this, which is 0, it is really a non-polar bond. But sometimes people will call that a pure covalent bond. So you'll sometimes hear people say that is a pure covalent bond. And what that really means is you have pretty much as perfect equal sharing of electrons as possible. It is still a nonpolar bond, but occasionally sometimes people will refer to it as a pure covalent bond. So if you see something that's called a pure covalent bond, it is a nonpolar bond. And, you know, you could treat it that way. But again, if you get that sort of difference that's exactly 0, some people do sometimes make that classification. If we look at our HF that we saw earlier, H is 2.1 and F is 4. So our difference in electronegativity value is 4 minus 2.1. Should have got the calculator. I'm going to go with 1.9. Correct me if I'm wrong on any of these. 1.9 is less than 2. It is between our 0.4 and 2. This is definitely a polar bond. We see at 1.9, that is darn close to 2, which means it is still hanging on, but there is definitely way unequal sharing happening. Those electrons are definitely hanging out closer to the fluorine in that case. Question on electronegativity here, how to use it. All right, so why don't you try some just to make sure. If you have the carbon-hydrogen bond, if you had, say, let's do calcium-oxygen bond. Let's do nitrogen-oxygen, and let's do nitrogen-chlorine. Take a second, use the values there, and figure out, are these bonds polar, ionic, or non-polar? So take a second there and try to figure out there what you come up with. Okay, so let's take a look here and see. We'll start with the carbon and hydrogen here. So if we look at carbon and hydrogen, carbon is 2.5. So we'll do carbon, hydrogen, we'll come down here. So carbon is 2.5 minus our hydrogen, which is 2.1. By the way, just do the larger minus smaller so you get a positive number. That is 0.4 for carbon and hydrogen in terms of the difference in electronegativity. So that should be a nonpolar bond. So carbon hydrogen is a nonpolar bond. And it is actually the reason why the cutoff is actually 0.4, because if you ever find yourself in organic chemistry, and I apologize, I'm sorry for you. I'm sorry, that's good. Organics, all right. But, you know, if you find yourself there, pretty much all organic molecules are carbons and hydrogens, and they're nonpolar. And so that's why we sort of have that cutoff of 0.4. Now, even though it's considered nonpolar, and even though it's considered perfectly equal sharing, or not really equal sharing of electrons, there really is an element of unequal sharing happening here. And really, for the lack of a better thing here, they are sort of heading a little bit towards the carbon, but not to an extent where it's considered a polar bond. So in reality, not perfect equal sharing of electrons here, still considered nonpolar and equal sharing, but there is obviously some unequal sharing that's happening there. If we look at calcium and oxygen, again, calcium is a metal, oxygen is a nonmetal, and really you didn't even need the chart, but just to verify here, calcium is 1 and oxygen is 3.5. So our difference in electronegativity would be 3.5 minus 1, which would give us a 2.5 difference. And obviously a 2.5 difference is ionic. Now, the cutoff of 2 is sort of a relative cutoff. It doesn't work 100% of the time. It's not perfect. You will have a metal and a non-metal that if you do the electronegativity and you subtract them, it may not equal greater than 2. But again, it is still really considered an ionic bond when you get a metal and a non-metal together. So you don't usually have to worry too much about it. If we look at nitrogen and oxygen, so I'll rewrite it over here. Nitrogen is 3 and oxygen is 3.5. So when we take the difference in electronegativity, that is 3.5 minus 3 gives us 0.5. 0.5 is above 0.4. So this would be a polar bond. And lastly here, if we look at nitrogen and chlorine, nitrogen has a value of 3. Chlorine has a value of 3. So when I do the difference in electronegativity, that is 3 minus 3, which is 0. This is actually going to be a nonpolar bond. Now you may say to yourself, they're different elements. They probably shouldn't be a nonpolar bond, but this does happen. And if you look at the relationship of these two guys on the periodic table, this is nitrogen, this is chlorine. They're sometimes referred to as being diagonal of each other. There's like a diagonal relationship. Carbon and sulfur also diagonal sort of relationship in terms of the electronegativity value. And the idea here is, although nitrogen is higher up on the chart, chlorine is further to the right on the chart, so they negate their differences and they actually do end up with the same electronegativity value. So it is definitely possible to have two different elements that actually does have the same electronegativity value, and they actually would make a nonpolar bond. If you have two elements that are the same, it's a pretty safe bet it is going to be a nonpolar bond. Now, the other thing that, you know, sometimes people are like, I need the table, I need the table, I always need the table. You don't really always need a table. You know, you could kind of figure out certain things without the table. So for example, if we look at the one that we did earlier with the nitrogen and oxygen are in the same row on the periodic table, which means further to the right should be more electronegative. So without even the table, because these guys are in the same row, you should know that it's going to be more electronegative on the oxygen versus the nitrogen. You don't actually even need the table to do that. If you were comparing, say, oxygen and sulfur, they're in the same group, which means if you go down a group, electronegativity decreases. So without even the numbers, you could figure out pretty safely that sulfur should have a lower electronegativity value than oxygen. So sometimes, you know, you don't really necessarily need the numbers all the time, especially if these guys are in the same period or the same group. You could use the general trend on the periodic table to figure it out. And probably 9 times out of 10, if it's two different elements, they're probably going to be some type of polar bond if they're both nonmetals. As long as you look at the periodic table, you don't have that sort of diagonal move, And again, that diagonal move does sort of follow, you know, all the way down a little bit. Again, you got kind of like the P and the TE here as well, you know, so you got that diagonal sort of thing. But in a lot of cases, you can almost just look at the periodic table and make pretty much a reasonable guess as to whether or not you would expect something to be polar or non-polar. And in terms of ionic, you don't even really need it at all. Like I mentioned several times, you could just use it, say metal, non-metal, check the ionic box and, you know, move on and stuff like that. Questions on electronegativity values, how to use it. Clearly you should memorize every number on there, and that's going to be a test. I am kidding, by the way. I can't see anybody's faces, really too many people's faces, but I'm kidding. Don't all drop now. It'll be okay. No, obviously, if you need this, it would be provided for you. If it's not provided for you, you probably could just use the general trend of electronegativity and figure it out. But again, if you did need it, it would be provided for you. The diagonal reasoning in terms of electronegativity is just sort of location on the periodic table. So for example, was carbon and sulfur. So if you look at where carbon is here on the periodic table. And sulfur is where I kind of scribbled everything right about here on the periodic table. Now, when we look at carbon, it's further up on the periodic table. So remember, electronegativity increases as you go up, right? So technically, carbon is higher up on the periodic table, but electronegativity also increases as you go to the right. So even though carbon is higher up on the periodic table, sulfur is further to the right. And that's why they call it sort of that diagonal relationship. That sort of difference in their location is enough basically to cancel out any differences between them in terms of electronegativity. So even though carbon's further up, sulfur is further to the right, and they sort of diagonally are related to each other, and that cancels out the differences. So they actually end up with the sort of same electronegativity value. Other questions on that? Okay. So like I said, it would be provided for you if you need it. It would be nonpolar, yeah. So for example, if we took carbon and sulfur, I don't know if I did that or not, but if we took carbon and sulfur, they both have 2.5 in terms of their values. So when we take the difference in electronegativity as 2.5 minus 2.5, which equals 0, it's actually a pure covalent bond, which is a nonpolar bond. That's actually perfect equal sharing of electrons that would happen when those two guys come together. Other questions on that? You're welcome. Now, before we sort of move off of this page here, just I want to remind you of something that we're really sort of talking about here. We use electronegativity for the most part to determine what is referred to as, I scribbled way too much on this page, we'll go back this way, in terms of bond polarity. Okay. So when you use those electronegativity values like what we were just doing, it is really, for the most part, going to tell you between these two atoms, not anything else in the molecule, there happens to be more bonds, but really just between these two atoms, is the bond between those two atoms polar, nonpolar, or ionic? Are they going to share those electrons equally, going to share those electrons unequally? And that's really what we're looking at here, which is bond polarity. And it shouldn't be confused with what we're going to talk about, not this chapter, the next chapter, which was referred to as molecular polarity. So molecular polarity is when we talk about the entire molecule as a whole, every single bond that's present, is that molecule polar or nonpolar? So again, typically what we use electronegativity values for, differences in electronegativity values, is what is referred to usually as bond polarity. And as we'll talk about when we actually do get to molecular polarity, in certain cases, it will tell you if it is polar or not, the molecule, or it will tell you if it does contain polar bonds. The only place where bond polarity and molecular polarity will come into play is when you have a diatomic molecule, like a couple that we saw. So for example, this one, we know that this bond between these two guys is a non-polar bond. But when we look at F2, there's actually only one bond in the entire thing, which means because that one bond in the entire molecule is nonpolar, this is also a nonpolar molecule. While if we looked at the HF like we did, we saw that this is a polar bond. But again, because that's the only bond in the entire molecule and it's polar, this molecule would also have to be a polar molecule. So the only place where sort of bond polarity and molecular polarity sort of cross over and can do the same thing is when we deal with this type of molecule. And hopefully you remember these type of molecules are our diatomic molecules, right? Basically a molecule that contains only two atoms. And because it contains only two atoms, it has only one bond. So it's really simple to determine if it's polar or not, the molecule, because if that one bond is polar, the whole thing is polar. If that one bond is nonpolar, the whole thing is nonpolar. It gets a lot more difficult when you have multiple bonds happening, and we will get into that great way of doing that in chapter 4 is where we actually get into that, okay? Any questions on any of that stuff there so far? Okay. So as I talked about, when we do get these guys that have really wide sort of variations in those electronegativity values, that's really when we're going to get that ionic bond that's going to happen. And again, that's because we got somebody on the left-hand side of the periodic table, somebody on the right-hand side of the periodic table. Very big difference in terms of those electronegativity values, ionization energies. You got people wanting to get rid of those electrons, accept those electrons. And obviously, when we get into just that small area of the periodic table where all of our nonmetals sort of live, they have those very similar type properties. And again, the best they could do is share. And as we see here with electronegativity, sometimes they will share equally and sometimes they will share unequally, as was the case with HF at 1.9, almost to the point where it's going to transfer, but it hasn't. They're still sharing, but super unequally there. So in general, as we've been talking about, what we usually will know here, again, an ionic bond being our metal and nonmetal, two nonmetals, going to be some type of covalent bond, and that covalent bond will either be nonpolar, equal sharing, or polar, unequal sharing. That's going to happen. And that's sort of our distinction that we were talking about, our sort of cutoffs. Not a lot of people still use sort of the bottom there, but it does pop up sometimes in books. So sometimes another way we could refer to sort of a bond is in terms of what is referred to as percent ionic character. So obviously, if you have a ionic bond, it has 100% ionic character, so that kind of makes sense. And if you have a nonpolar or a pure covalent bond, you have something that is 0% ionic. And that would be a case where we have a difference in electronegativity value of 0, basically will give you that 0% ionic character. Anything kind of 2 and above in terms of our difference in electronegativity will give us 100% or near that 100%. And obviously a polar guy would be somewhere in the middle there in terms of the percentage. Most people these days don't usually use too much of the percent ionic character. We talk about the bonds either being polar or non-polar or ionic. That's usually what we do. And as I mentioned earlier, again, the cutoff, and especially the 2 cutoff there, it is just sort of a general sort of cutoff. It does really sort of work with most things, but if you look really hard at the differences in those electronegativity values between the metals and the non-metals, you'll be able to find one that actually is not above 2 or something like that. And there you go, intermediate as well. So then let's talk about how we go about actually drawing Lewis structures for covalent compounds. So I'm going to walk you through really, I won't say the right way, but probably the best way to sort of do Lewis structures or draw Lewis structures. And if you follow these steps, you really should end up with a Lewis structure that is probably a pretty good one. If you follow what a lot of people try to do, and I'll explain it now, and it might not make sense what I'm going to say, but maybe it will. What a lot of people will try to do when they go to draw Lewis structures is they'll take all the pieces individually. So they'll take all the elements, they'll do all their little dots on their Lewis dot symbols, and they try to figure out, all right, this electron goes there, this one goes there, this guy needs 2 electrons, 3 electrons. And you sort of do it in sort of piecework, if you will. And usually what will happen is you'll end up with a picture that either has too little electrons, too many electrons, too many bonds, and all those type of things. If you follow these steps here, it should pretty much lead you to a pretty decent Lewis structure every time. So let's talk about sort of the steps along the way that you should do. The first thing is you should think about logically how the structure is arranged. And there's some things that could help you decide, for example, what should go in the center, what should go on the outside. And that's sometimes what is referred to as sort of the skeletal structure. In general, the least electronegative atom will end up in the middle of the molecule. So when you go to draw a Lewis structure, usually your least electronegative guy should occupy the center position. In most cases, probably everybody else should be kind of attached to it. And with our least electronegative in the center. That means that we do not find hydrogen in the center, nor do we find fluorine in the center. We don't find fluorine in the center because, as we just saw, it is the most electronegative atom you could have. So it never usually occupies the center position. And we cannot put hydrogen in the center because if we put hydrogen in the center and it's attached to one or two other things, my good friend hydrogen has way too many bonds at this point. So because hydrogen can only have 2 electrons, it always is on the outside looking something like that, again with no dots on it or anything like that. Otherwise, if you put hydrogen anywhere in the inside, it's going to end up with too many electrons and obviously too many bonds. I would say other than that, the next super important thing right here, that's that scientific word, super important, is to count the total number of valence electrons that you got going on in your structure. And that number is really important because when you are done with your picture, you have to hit that number exactly. You got to have exactly that number of electrons. You can't have one more electron than that. You can't have one less electron than that. We also, when we're counting the valence electrons, need to take into account anything that may have a charge. So if something has a negative charge, the way that we become negatively charged is that you gained electrons, which means we need to add that charge to the total. Also, if something has a positive charge, we need to subtract that positive charge here. Do a little correction there. Positive charge from the total. So again, if in order for us to become positively charged, we had to lose electrons, so we need to subtract that. And again, that number is really the most important one because that tells you exactly to the nose what you need to do. Now, the next step that you should do, if you want to end up with probably a good structure, is you should go from the center atom to each of the outside atoms and make one single bond. I personally use lines, so you want it to go from your center guy to all the outside guys and just make one single bond like so. If you want to use dots, you can. This is really important because people, for some reason, always want to double bond and triple bond right out of the gate. Just keep throwing lines on it and hope for the best. So you really shouldn't do that. You should probably single bond first. Once you've single bonded, you want to count up how many electrons you used. Each line represents 2 electrons. You want to subtract that from your total. And then any leftover electrons go on the outside ones in pairs, not singles, but in pairs, until the outside ones are full. And again, to get the outside ones full, we need 8 electrons unless it's hydrogen. Go to the next outside one if I still have electrons and make sure that guy is full. If you happen to have filled up all the outside ones with electrons and you still have some electrons to go, then you go to the center and put electrons on in pairs until you run out of electrons. At some point, you should run out of electrons. And at that point, what you want to do is make sure that everybody has met the octet rule, which means everybody has 8 electrons around them, except for hydrogen that should only have 2. If you see somebody has not met the octet rule, that is the place where you then should double bond to try to fix it. So you should try to do all the double bonding you can to try to fix it. And if the double bonds don't fix it, then you should triple bond and try to do some triple bonding to fix it. And if the triple bonds don't fix it, you probably screwed up. I'll be honest with you. You should probably be done with the triple bonds at that point. You shouldn't go any further than that. But that's really where you should do it. So again, for some reason, people always like to just right out of the box, I'm just going to start triple bonding, double bonding stuff because, you know, it looks cooler. There's a lot more lines, you know, a lot more fun things to do on there. I don't know. You could draw a hat on it, whatever you want to do. But you really should save that to try to fix a problem. And in most cases, that'll give you sort of a better structure. May not always give you the best structure when we're going to talk about in this chapter how you can determine whether or not one structure is maybe better than another. But it will usually give you a pretty good structure. So let's talk about or go through one here together since we're getting to the end and sort of go through these steps and sort of show you how to do it. Actually, why don't you take a second here and give it a go, and then I will show you sort of the way we were just talking about there. Okay, so let's go through the steps just to make sure here. So again, first thing I usually do is get the total number of valence electrons. So we have NF3. Nitrogen is 5, group number 5 from the periodic table. There's 3 fluorines. Fluorine is group 7. Really should have grabbed that calculator, but that's like 21 and 5. We'll go with 26. We'll hope for the best. There we go. Clearly in this case, usually if you have one element and 3 of something else, that one element's in the middle, everybody else is attached to it. Also in this case, the 3 guys are fluorine, which is the most electronegative. So in terms of just skeletal structure here, nitrogen should be in the middle, fluorine should be on the outsides. Does not matter if you put the fluorine on the bottom like I did, or if you put the fluorine up on top, it's all good. You could do it either way, it doesn't really matter. Now, I'm going to make one single bond to all of the outside atoms. Again, I'm going to use lines. If you want to use dots, you can. I'm going to use really badly drawn lines there. That is 2, 4, and 6 electrons that I've used by making those 3 bonds. If I subtract off from my total, which again is the total number of electrons I need to have in my picture, I got 20 more to go. They go on the outside ones in pairs. So each of the outside ones have 8 electrons, except for hydrogen, which we don't have in this case. So I'm going to go here. So that's going to be 2. That's going to be 4. That's going to be 6. That guy is full. That's going to be 8. It's going to be 10. That's going to be 12. That one is full. Counting, that's 14, 16, 18. So at this point, I have now filled up all the outside ones. If I count up the total number of electrons that I've just used, I just put on there 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. That leaves me 2 more electrons to go. Since I've already filled up everybody on the outside, that is when I go to the center and put them on again as pairs. And now I have a grand total of 26 electrons. The last thing I want to do is make sure everybody has 8. Fluorine on the right here, 2, 4, 6, 8. All the fluorines are identical to each other. They all have 8. And my good friend nitrogen here in the middle, that is 2, 4, 6, and 8. So it also has 8 as well. And that means everybody is happy. Everybody has the octet rule met. We have used only our 26 electrons. And this would be the correct Lewis structure here for NF3. Any questions on that there? Yeah, so that is honestly really the whole goal of bonding, covalent bonding, ionic bonding, because 8 valence electrons essentially moves everybody to the noble gas configuration, and it gets those elements in that super stable situation in terms of electrons. And again, the reason why hydrogen only needs 2 is, if you look on the periodic table, right after hydrogen is helium, and that's a noble gas, and helium's only 2 electrons. So all hydrogen needs is just 1 more electron to get to that very stable situation. So that's why hydrogen only needs 2, and everybody else, no matter what the situation, there are some exceptions we'll talk about at the end of the chapter, but for the most part, 99% of the time, everybody wants to get to that 8. Any other questions on any of that? Okay, so we'll lay it up there for lecture for today. For lab, we're going to talk about all that kind of stuff, sig figs, conversions, all that. Just make sure everybody's on the same page. The study assignment involves all that as well. So we'll do a little short review lecture on all that topics, and then you can do your study assignment. Again, a reminder, quiz on Tuesday on chapter 1 and 2, and make sure that you have taken that proctorial, whatever that thing is called there, that proctorial, I'll spit it out, practice quiz. Again, I think it's due tomorrow. If you haven't done it, you more so, A, is worth points, but B, so you will be all set up to take the quiz on Tuesday for something real. And I will not have sympathy for you if you did not take advantage of doing that and you tell me on Tuesday, I don't know how to do it. I'm going to tell you, tough luck, yes? So make sure you take care of all that so you get yourself set up and you're good to go on the real quiz. All right, I'll see everybody about 7:15. Make sure you put here if you haven't done so. And I'll see everybody in the lab one in about 15 minutes or so.